This is the last group, 37 through 40. If you're looking for number 36, it's in the last group, which is labeled 31 through 35, but it's actually 31 through 36. Okay, here's 37. They want how far this car, total distance traveled by the car during the 6-second interval. Okay, on a velocity time graph. I want to find the area under the graph, which I'm drawing as two separate areas, a triangle plus a rectangle. If you're crazy, you can go trapezoid and find this area by finding the area of a trapezoid. I'm going to do it as two separate pieces. I'm going to do the triangle part first. 1/2 base times height. That is 1/2. Okay, the base of this triangle goes from 0 to 4. So the base is 4 seconds. The height of the triangle is 10 meters per second. Half times 4 times 10 is 20 meters. The seconds cancel out. The rectangle part over here is simply base times height because it's a rectangle. The base from 4 to 6 is 2 seconds, and the height is 10 meters per second. And we get 20 meters. Again, the seconds cancel. To find the total distance, I just add those up, and I get 40 meters, which is choice C. Okie doke. You could also, I'm not going to do it, you could apply average velocity times time to each of those two halves, the 0 to 4 and the 4 to 6, and get the same result. Moving on, 38. Looks like a centripetal something is going in a circle. They want centripetal acceleration, and so I'm going to say the centripetal acceleration is v squared over r. They give me the mass of the stone. I don't care. All I want is v and r. The v is the speed in meters per second. That's 4.0 meters per second. I'm going to square that because I have to, divided by 0.80 meters. And so I do the math. I do 4 squared divided by 0.8, and I get 20. AC is equal to 20 meters per second squared, and that is choice D, as in D. Okay, last page, 39. 39 says, okay, what's the direction of the centripetal force? It's the same as the direction of centripetal acceleration, which is inward toward the center, that is toward point C. I think that's all we have to say about that. Inward toward the center for both force and acceleration. And finally, number 40. So we have, I'm going to do a quick sketch here. This is the direction this thing is traveling. They draw the arrows because it's going clockwise. The ball is over here. They draw the string like so as this thing goes around a circle. And they have a target kind of down here somewhat. And the basic deal with this problem is this. You're going to release the ball at one of these points. So in other words, it's going to stop accelerating. You're going to cut the string, release the string. So if the ball's at point A, for instance, when the ball is at this point, its velocity is tangent to the circle. So if I cut the string at that time, the ball is going to just not accelerate. It's going to have that velocity forever. It will miss the target. If I release it at C, which is kind of over here somewhere, okay, the ball's going in a tangent to the circle. The velocity is tangent to the circle. So if I cut the string when it's at C, the ball's going to go forever. It's not going to accelerate. It's going to keep on going that way forever, and it's going to miss the target. The magic point here, and you know it's magic because it's green, is point B. Because when the ball is at B, its velocity is tangent to the circle. And I can cheat a little bit, but if you look at their diagram, this actually works. Tangent to the circle, it's going to go in that direction forever. If the string is cut at point B, it's going to hit the target. You're going to get little lines that tell you that it hit the target, and it makes you happy. So the answer is choice B. All you can be. Thank you very much.